All right, today we're going to look at series and convergence for a second day, and we want to come up with the sum of these different series. So we're looking at the series sigma n equals 1 to infinity of 3 times 0.85 raised to the n minus 1 power. So what we need to do is recognize that this is the number 3, right? And we're multiplying by powers of 0.85, which makes this a geometric series, because when you repeatedly multiply by the same amount, in this case 0.85, that's called a geometric series. And we also look at what are we multiplying by each time? 0.85. Now that's between -1 and 1, so that means it has to converge, okay? And so we would say, okay, so this is the geometric, we would say this is a geometric series with r equal to 0.85. And then since, and we need to write it up like this, okay, so since -1 is less than 0.85 is less than 1. So if our r is somewhere between -1 and 1, then by the geometric series test, so we got to name the test we're using to say that it's converging. So by the geometric series test, the series converges. Okay, so this is one of the cases. Most tests that we're going to do, we just know it converges. We don't know what it converges to, but a geometric series is special because we can actually tell what it converges to. We know what this sum is going to become. All right, so n equals 1 to infinity of 3 times 0.85 raised to the n minus 1. Okay, so what this is the sum will always be, if the r is between -1 and 1, the sum will always be the first term. So if we put 1 in here for n, that's going to make this a power of 0. So that's just going to give us for our first term 3 over, and it's going to be 1 minus our r, which is 0.85. So it's always the first term divided by 1 minus your r. Okay, so that winds up being 3 divided by 0.15. If we had a calculator, we could just put it in our calculator, but if we don't, we could write this as 3 over 15 over 100. Okay, and then that would be 300 over 15, and that's 20. So this series converges, and it converges to 20. Okay, so the other thing we're going to look at, and we're going to use a calculator for this, and I'm going to switch over to the calculator in just a minute, but we're also going to want to find and finish a table, and we're also want to graph this. I'm going to show you how to do that, how to build a table of the partial sums and also graph the partial sums. And I'm going to show you how to do that on the graphing calculator. All right, so let's go to do that next.
So the very first thing we want to do is press the mode button on our calculator, and we want to make sure we're in sequence mode. So we want to come over here about the 5th line down. We don't want function highlighted, we want sequence to be highlighted. So press enter on that, then we can quit. All right, so to add the first 5 terms of a series, what we can do is, I don't believe I've shown you guys this. You press alpha window, and then number 2, it's the summation. Okay, and because we're in sequence mode, this is not going to be x, it's going to be n. All right, and we're going to start it at 1, and we want to add the first 5, so we want to end it at 5, and then our formula is going to be 3, and then times the 0.85, and then raised to the, and then n minus 1. So when you're in sequence mode, it gives you an n instead of an x. Okay, if we press enter, we get 11.1259. So that's the sum of the first, the partial sum of the first 5 terms of this series. Okay, so let's go back and let's record that on our paper.
So from our calculator for our first 5 terms, the sum of the first 5 terms, we got 11.1259. Okay, so let's go back to our calculator and do it for 10.
And then for the first 10 terms, again, press alpha window, and then select number 2 for summation, and then n equals 1 to 10. And again, we can do 3 times. You could also, move up here and highlight this and then type over 5. I'll show that in the next one. 0.85, and then raise to the n minus 1. and this gives us 16.0625, and that's the approximately the sum of the first 10 terms of this series. Okay, let's go back and record that on our paper.
And then for the first 10 partial sums, this one would come out to be 16 from our calculator, 16.0625. And then let's go do the first 20.
So for the first 20 terms, I'm going to come back up here. I'm going to highlight this and then press enter. And then all I'm going to do is go back and then type over instead of 10. Whoops, a little too far. We want to type in 20 for the ending term. And for this one, we get 19.2248 for the first 20 terms of the series. And so then let's go ahead and do 50 and 100 while we're right here. So let's go back up and highlight. And for the first, whoops, I always go a little too far. So 50. And so for the first 50 terms, the sum is 19.994. And then let's do the first 100. So again, you can go up, highlight that sigma notation, and again, I went too far. 100, right? And the first sum of the first 100 terms is 19.99999, 4 nines, right? So this looks like it's growing. It's still growing, but it's not growing as much now, right? So it looks like it might be approaching something, okay? So let's go back and then let's record these values in that table for part B of example 1.
So then for the first 20 terms, it'd be 19.2248. I'm going 4 decimal places, but really you'd only need to go 3 for the AP exam. Okay, so now let's jump. Let's go all the way to 50, the sum of the first 50 terms. So the sum of the first 50 terms was 19.9941. And then let's find the sum of the first 100 terms. So the sum of the first 100 terms from our calculator was 19.9999. So it looks like what we're getting up here, it looks like we're approaching 20, right? Okay, so now let's go and I'm going to show you how to enter this into the graphing calculator and how to graph the first 10 terms of the sequence. Okay.
So back here on our calculator, we want to graph the first 10 terms of the sequence of partial sums. Okay, so what we want to do is we go to y equals, and we want our first term to be 1 because that's what our series starts with. It was n equals 1. And so for u sub n or u of n, that's going to be the series, the terms of the series, okay? So this is going to be a little different, but we have to go back and do the summation, number 2, okay? And we're going to type in, and we can't start it at n equals 1. We want it because we want to end it at 1. All right, so we're gonna call this one, I call it K probably. So you got to pick a different letter. So K equals 1, and because we're gonna want to end this at n, okay? What this will do is K is now our variable. N just represents the nth term. Okay, so then we're gonna come over here. We're gonna type in 3 times and then 0.85. Close parenthesis, and then raise this, but it's not going to be K because it's going to be K minus 1 because this is our variable that we're finding or using, okay? So alpha K minus 1. And then we got to set up our window. So we know we're approaching a sum of 20, right? So we want to n min, that's going to be 1, and then n max is going to be 10. Our x min, since we're starting this at 1, our x min should be 0, and x max should be 10, and scale by 1s, and then y min should be 0 because the sum only goes up to 20. So let's put this at 25 for the y max, and then y scale, let's go by 5s. Okay. And then let's go ahead and graph this, and this is what the sequence looks like. So as you can tell, it's I don't think we're going out quite enough terms to see it, but this is 5 right here, and this is 10, 15, and 20. Okay, if we go out further and further, right, if we instead go to an in max of, let's say, 20, okay, that means our x max would have to also be 20. And we graph that. So now we're starting to see like it's starting to approach it, right? And then we can do 50, right? So if we go to window and we go to 50, and that means we need to change our x max to 50. And now I probably change my x scale to 5s and graph that. And now you can start to see that it's flattening out, right? It's approaching a value. That's the converging part, right? And I also ask you to graph the horizontal line. We can't really graph a horizontal line in this format, but we come down here, and we can just type in a sequence that's 20. V-sub is always 20. And so we can see that the sequence of partial sums is getting closer and closer to this value of 20, and the graph really shows that now. Okay, so that's what I want you to do. If they ask you to graph it, I don't want you to necessarily graph it by hand. I just want you to know how to use technology and graph the sequence and see that it's converging to something. All right.
So for this next problem, okay, we got to realize that this series is not necessarily a geometric series. So what techniques, what can we grab and use and figure out whether this converges or not, okay? And so what we have to realize is that this is a product of binomials down here. And so this comes from partial fraction decomposition. So we can break this out and rewrite it as the sum or difference of two fractions. So that's the first thing we got to do is, and when that happens, remember we talked about these telescoping sequences. So we're going to take a look and see, okay, is it one of those? And then we're able to simplify this, okay? So we're going to take 1 over 2n plus 1 times the 2n plus 3. And we're going to break this up. So it's going to be some numerator over, we're going to call a over 2n plus 1. And then plus some numerator b over 2n plus 3. So we're going to multiply to clear out all of our fractions. So that's going to give us 1 is equal to a times, and it would be 2n plus 3. So I'm multiplying both sides of this equation by the 2n plus 1 and the 2n plus 3. And then plus b times, and when I multiply this by the two denominators, I'm going to be left with 2n plus 1. Okay, so we're going to let n be, in this one, we're going to let n be -1/2, because that's going to cause this to be -1. So, and that will give us our b value, okay? Or I'm sorry, it'll give us our a value. N is equal to -1/2. That means this is going to be 1 is equal to a times, and then -1/2 times 2 would be -1 plus 3. So that'd be 2. And then plus b times, and then this one's going to be -1 plus 1. So that's going to be 0. So that tells us that a is going to be 1/2. To get rid of this one, in order to get the b value, okay, we're going to let n equal -3/2. Okay, so that's going to cause this to become -3. All right, so that's 1 is equal to a times, and this one would be 2 times -3/2, which would be -3 plus 3, that'd be 0. And then plus b times, and this would be -3 plus 1, which would give you -2. And this one drops out. So we're left with b times -2, or b is equal to -1/2. Okay, so that means we can rewrite this as 1/2. And instead of plus, I'm going to write minus, and b's -1/2. So instead of writing plus a -1/2, I'm just going to write minus, and then the b is going to be 1/2. So this becomes 1 over 2n plus 1 times 2n plus 3 is equivalent to 1/2 over 2n plus 1, and then minus 1/2 over 2n plus 3. And this created a complex fraction. So I'm going to multiply by 2 over 2 for this fraction, and also 2 over 2 for this fraction. That's going to give me 1 on top for this one. This one's going to become 4n plus 2. Then we have the minus, and multiply this one by 2 over 2, and this numerator becomes 1 over, and this one becomes 4n plus 6. All right. And now what that does is it allows us to rewrite this form of the summation as the difference between these two fractions. Okay. So that means this series, n equals 1 to infinity, of 1 over 2n plus 1 times 2n plus 3 can be rewritten as sigma n equals 1 to infinity of 1 over 4n plus 2 minus 1 over 4n plus 6. And just look at this, we don't know, we really don't know where this is going to go. Okay, so we have to go out several terms. Okay, so let's look at S sub n, the sum of the n partial sums, I think I said that wrong. So the partial sums, all right, is what we're going to do. And so if we put 1 in here, okay, so this is going to be 1/6. And if we put 1 in here, that's going to be minus 1/10. And then we're going to add to that. Okay, so now we put 2 in, right, for the second partial sum. Okay, if we put 2 in here, this is going to be 8 plus 2, which is 10. So that's going to be 1/10. And if we put 2 in this one, this is going to be 8 plus 6, which is 14. So minus 1/14. And then plus, so then if we do 3 of these, it'd be 1 over 14 minus 1 over 18. And then plus, and I'm going to do the fourth one. So if we do the fourth one, that'd be 1 over 18. And then minus, and then if we put 4 in this, this would be 16 plus 6, which is 1 over 22. And we start to see a pattern, right? This one is minus 1/10, but then we're going to add 1/10. This is minus 1/14, then we're going to add 1/14. Subtracting 1/18, then we're going to add. So these are going to cancel each other out, right? So plus dot 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 plus, and the last one, the nth one, would have to be 1 over 4n plus 2 minus 1 over 4n plus 6. So this allows me to rewrite the sum of the nth partial sum a different way. Okay, because I know this one and this one are going to cancel. So the last one in the parentheses is going to cancel with the first one of the next one, right? The last one here is going to cancel with the first one here. Last one here. Okay, so this one right here is going to cancel with the one before it. So we're not going to see this, and we're only going to have 1/6. So this one's going to cancel with this one. These two are going to cancel. These two are going to cancel. This would cancel with the first one of the next term that we're not writing. And then that last term here would cancel with this one, right? So all we'd be left with is 1/6 minus 1 over 4n plus 6. So that's a formula for the nth partial sum of these, okay? If we let n go to infinity, then that's going to allow us to figure out what the actual sum is, if it even exists. Okay, so let me slide my paper up a little bit. So we're going to write sigma n equals 1 to infinity of 1 over 2n plus 1. We're just writing the series again, times 2n plus 3. This is the same as the limit as n approaches infinity of the nth partial sums. Okay, and this is always going to be true. Okay, and if this one converges, then we know this one converges. Okay, this the nth partial sum is really this formula now, right? We came up with a formula for the sum, not just the series, but the formula for the sum. So then this becomes the limit as n approaches infinity of this 1/6 minus 1 over 4n plus 6. And we should realize that this is the forehand is controlling it, right? And as n goes to infinity, this denominator is going to get really, really big, which is going to make the fraction get closer and closer to 0. So really doing 1/6 minus 0. So that means this converges to 1/6. So this series converges, the series converges to 1/6. All right. And that's how you do these. It's just good to see these one more time. Okay. All right, let's do another problem. So here's a series, just a series of numbers, 8 plus 6 plus 9 halves plus 27 eighths plus ... And that means it's going to go forever. This pattern is going to go forever. Does this series converge? And if it does, what's the sum, right? So if you look at this, we got to think of different things. Okay, so if we're going from 8 to 6, so that's subtracting 2, right? We could look at it like that. Okay, but then the next number would be 4. It wouldn't be 9 halves. So that doesn't work. It's not an arithmetic series, okay? Is it a geometric series? Because if it's a geometric series, then we're going to be able to see if it converges by the geometric series test, right? So the way to tell if it's a geometric series, let's take this term 6 and divide by the previous one. Okay, so that would be 6 over 8, which 6 over 8 reduces to 3/4, and that would be our R. Now, if we do this every time and we get the same thing, then we know it's a geometric series. That means we're multiplying by 3/4. Okay, so to get to 8 to 6, if we multiply by 3/4, 3/4 of 8 is 6. Okay, so we got to do the same thing we're going to take this term 9 halves and divide by the previous one. So that'd be 9 halves divided by, that's a 9 right there. Let me erase, let me get my white out. Let me fix that so you can see it. Okay, so this is 9 halves, and we're going to divide that by 6. So that's really, I'm going to multiply by 2 over 2. That gives me 9 over 12. But then 9 over 12, well, that's 3 over 4 because 3 goes into both, right? So that one's also 3/4. Okay, so let's double check. Is the next one, okay, so we're going to take 27 eighths and divide that by 9 halves. So I'm going to multiply this one by, I'm going to write this one this time, 8 over 8. That gives me 27 on top over, and on the bottom, it would give me 36. And 9 goes into both, so that'd be 3/4. So yeah, we're multiplying by 3/4. To get from 8 to 6, we'll multiply 8 by 3/4 and we get 6. If we take 6 and multiply by 3/4, we get 9 halves. If we take 9 halves and multiply by 3/4, yeah, we get 27 eighths. Okay, so that means the series is the first term. We can actually write this in sigma notation. So this would be sigma n equals 1 to infinity. Our first term is 8. So it'd be 8 times what we're multiplying by is 3/4 raised to the n minus 1. Now, why does it have to be n minus 1 and not just n? It's because I want my first term to be 8. And if this was just n, then what that would cause me to do is my first term, I would have to multiply by 3/4. So actually that would cause my first term to be 6, okay, and not 8. So if you have n minus 1, if you start this at n equals 1, that's going to be a power of 0. And because it's 3/4 raised to the 0 power, that's 1. And so it'd be 8 times 1. All right. Okay. So what we know now is that this series, n equals 1 to infinity of 8 times 3/4 raised to the n minus 1 is a geometric series with r equal to 3/4. So we need to write this up when it's a geometric series. Okay. Now we're looking at r. So we know that's between -1 and 1. Then we know the series converges by the geometric series test. So we need to say that. So since -1 is less than 3/4, which is less than 1, the series converges by the geometric series test. Okay. And the geometric series test is the only test that actually, again, we can know what it converges to. There's a formula for it. So sigma n equals 1 to infinity of 8 times 3/4 raised to the n minus 1. It will always equal, if this r is between -1 and 1, the series will be, the sum of the series would be 8, which is the first term, divided by 1 minus 3/4. Okay, so that would be 8 divided by 1/4, or 32. Okay, so this series converges because it's geometric series test with r being 3/4, and then that r is between -1 and 1, and this is the formula. It's the first term divided by 1 minus your r value, your common ratio. All right, let's do another problem. So there was another test that we learned, and it was the nth term test. Okay, and the nth term test said that if you find the limit of the terms of the sequence, right? If you find the limit and that turns out to not be 0, then we automatically know that series diverges. So it's called the nth term test. It's actually a test to show that something diverges, okay? Not converge. Most of the tests we have are for converging. This one's actually for diverging, and it can't equal 0. If it equals 0, it doesn't tell us anything. It's inconclusive. We have to use something else, okay? So what we're going to look at is this. We're going to take a look at what's the limit as n approaches infinity. This is definitely not a geometric series test, okay? And it's not a telescoping one, okay? Because that's where you're going to be adding. A telescoping one, you're going to be either adding or subtracting two fractions, okay? That's why we had to do partial fractions earlier. Okay, so for this one, we're going to find the limit as n approaches infinity of n plus 1 over 2n minus 1. And you want to do this a lot of times when you have n in the numerator and n in the denominator, okay? So if you take a look at this, this limit is equivalent to finding the limit as n approaches infinity. This plus 1 and the minus 1 are really insignificant. So this becomes n over 2n. And there our n's cancel, and we're left with the limit as n approaches infinity of 1/2. Well, it's going to be 1/2, right? Now, because this isn't equal to 0, it's actually equal to a number value, right? This limit. That means by the nth term test that the series must diverge, okay? So you have to write this up and say, since the limit as n approaches infinity of n plus 1 over 2n minus 1 does not equal 0. That's the part that we have to have, right? It has to not equal 0. Then the series diverges by the nth term test. So this is one, I mean, it's really easy to get confused and think, oh, if it goes to 0, then that means it converges. And that's not true, okay? Not necessarily true. It could be true, but it doesn't have to be true, okay? All right, let's do one more problem. So we want to determine the convergence or divergence of this series, okay? So what we have to recognize is that we can rewrite this. So this is the same as sigma n equals 0 to infinity, all right? And it's because this one starts at 0, this one's going to start at 0. And we got to realize, okay, this is 1 over 4 to the n, but this could also be written as 1 to the n. So this could actually be written as 1/4 raised to the n power, okay? So what does that mean? That means we have powers of 1/4, right? So we're going to be multiplying by 1/4. Okay, so we're multiplying by the same thing each time. That's called a geometric series, right? So this is a geometric series. With r equal to 1/4. And since -1 is less than 1/4, which is less than 1, right? It's between -1 and 1. Then that tells us this series converges by the geometric series test, okay? So the series converges by the geometric series test. And because it's a geometric series, we actually know what the sum's going to be. Okay, so it's going to be sigma n equals 0 to infinity of 1 over 4 to the n power, because that's the original series that we started with, right? All right. What is the first term? So this is telling us we got to put 0 in for our first term, right? So if we put 0 in, that'd be 1/4 to the 0 power. Well, that'd be 1. So our first term is 1. So that'd be 1 over 1 minus 1/4, right? Because it's 1 minus your R value, and our R value is 1/4. Okay, so this becomes 1 over, that'd be 4/4 minus 1/4, or 3/4. This converges to 4/3. And if we were able to add them all up, it would come out to be the number 4/3. Okay. All right. So that's how you do these problems. Okay.